First of all, I want to say thank you for attending the webinar here today on leveraging residual stress after heat treatment. All right, so let's get started here. Today for the outline, we have a little introduction to DANTE and heat treatment modeling in general. And then we have a little bit of introduction on the residual stress itself, modeling results, like quantifying the modeling results. We have a couple examples here about the general workflow. We have the map solve feature in Abaqus and Ansys, and how we bring the residual stress from the heat treatment models to other loading models. We also will talk a little bit about mechanical properties and residual stress validation. And then we'll have a couple case studies where we show how we actually employ the residual stress mapping and some conclusions. So to start out a little bit on DANTE solutions, DANTE is an acronym for Distortion Analysis for Thermal Engineering. We were founded in 1982 as Deformation Control Technologies. So if you see a lot of papers from those regions, they would be under DCT. We've been focusing on heat treatment simulation software ever since the 1990s, when we were part of a large collaborative effort between industry, academia, and the national labs to predict distortion. And that ran through the 90s, from 92 to about 2000. And the main thing was the need to control distortion and scrap. So DANTE Solutions has sole ownership of the software that came from that project, and we've been responsible for the development ever since 2000s. We've had a lot of different additions and updates over the years, and we continue to do so every year with a new package. Our main lines of business are the software licensing, the heat treatment technology development, and we also do a lot of technology consulting services with our software. We're located right in the shores of Lake Erie here in Cleveland, Ohio, and here's like the 6 main people who work here. I'd like to meet you sometime. So a little bit about heat treatment modeling basics. So heat treatment is a very complicated process. But it really encompasses 3 main areas: heat transfer, deformation, and phase transformation. And when you're modeling these, they have a lot of interdependencies, leading to a lot of nonlinearities in the process. So it makes it a little bit difficult to model. When we talk about heat transfer, we have like a lot of temperature-induced transformations. So if you can see on this little GIF here, we have like a heating, and as you heat up, your strain increases. Obviously, the part gets larger here. But when you have a phase transformation, we have a little bit of a strain here, and this would be a transformation to austenite. And this would be associated with a volume shrinkage, because austenite is a more dense form of steel, crystal form of steel. And then on the same way, during cooling, you can transform to diffuse phases, but here we're showing martensite transformation, and we have a volume expansion from that martensite transformation. And so that transformation, that heat transfer, has an effect on the transformation here. And then the volume changes from those transformations is the phase transformation to deformation. Linking heat transfer and deformation, we have thermal expansion, which we showed with these nice straight lines here, the coefficient of thermal expansion. We also have some heat generated from plastic deformation. You can see that in like forming processes and stuff like that. So all these are interlinked to lead to the heat treatment model. Our models also include the phase transformation models, the multi-phase mechanical models, trip models. We have a mixture law for like mechanical properties and hardness and stuff, depending on the phases. We have tempering models. We just developed a carbon partitioning model, which kind of governs the stabilization of austenite. We have carburization models, nitriding models, and all sorts of other models built inside of DANTE. When you get DANTE, you kind of get this package here in the DANTE directory, and this includes your licensing and equipment, user database, which I'll talk about in a minute, and then whatever version we're actually running here. Now, the full FEA package works with Abaqus and Ansys, and this is included in these folders here. Each one of these, whether you use Abaqus or Ansys, they include examples, generic HTC data, an install test to make sure everything's running right, and various tutorials to make sure you can build heat treat models effectively. We also have standalone utility tools, which are like little snippets of the DANTE code, and each one of them does like a little specialized niche of the actual full FEA software. And we have a robust standard database, which I'll talk to here in a minute. Pictured is one of our utility tools in the last webinar. If you missed that one, it's on our YouTube. This one depicts the heat treatment process simulator, the HTP sim, which can show basically the entire heat treatment process thermally, and the results from that, like phases, hardness, and such. For the DANTE material database, like I said, we have a robust database with over 70 or so standard materials. They each come in these little folders here, and you can see some of them have like 10XX. That means it's a carburizing grade, which means we have carbon levels throughout from the base carbon to all the way up to like 1080, 1090 or something like that. Inside each one of these folders, we have phase transformation kinetics to govern the transformations to austenite, martensite, or diffusive phases. We have plasticity mechanical properties. We have coefficient of thermal expansion and transformation strain data, and then any hardness related properties of the individual phases or iron carbides, coarsening models, and such. Users can develop their own materials for their own proprietary data. So say we have something close or you have something that's a little bit different than what we have here, we can create your own material and you can run those, and those are your own proprietary materials there. And here's some commercial examples of parts modeling by DANTE. You'll see a lot of gears. That's kind of like I'd say a large portion of our business is modeling gears here, but we also do, like scanning induction for like automotive shafts, bevel gears, carburized aerospace spur gears here, complex, powder met gears that were created here. We do press quench processes like the ones down here, this bevel gear here, these little gray pads here would be the pads on the press quench. Oil quench gear shaft is pretty similar. We have crankshafts that were induction hardened that have like little pieces of geometry, which could be stress risers. And then we also do stuff really large, like large 300M landing gears, where the immersion process is really important for these type of gears. You can see here the bottom is more blue, which means it's a cooler, and then it's probably immersed to right around where this red line is here in whatever quenching it is. And as we quench, we will have that scanning up the part in the quenching direction. So that's really important for like the large gears. Smaller gears that get dropped in the tank really quickly are usually not as important. So a little introduction to what we're doing today. So typically loading models simulate the part performance like fatigue or overload. And a lot of times they use these without considering residual stress or mechanical properties from heat treatment. Heat treatment can significantly alter this residual stress in the part, especially in case hardened parts that typically have a compressive residual surface stress. Carbon dependence properties is a big thing as well in the carburized case parts. Yield strength and modulus elasticity are also phase dependent, so depending on what phases that you have there, these might be different. And then since most critical parts are hardened, since most gears are hardened in industry, these quantities should be considered in loading models. And so the big challenges and key points of this whole presentation here is being able to predict the residual stresses and the material condition after heat treatment, and then be able to map these quantities into a loading model that you can use and effectively see the differences between them. Here we have a little bit of a contour here that shows the heat treat residual stresses that are developed in the case hardened parts. And you can see the subsurface here in this martensite contour where the carbon is low and the temperature is low during quenching. The martensite will start first here in the core and then work its way towards the surface, leading to that compressive residual surface stress we were talking about. So the model results, this is kind of like what we put in and what you get out here. So a lot of times, meshing templates aren't exactly the thing, but meshing is really like an art form, and knowing where to put the elements is really good. For our models, we really like to have fine surface elements near the surface of the part to capture the chemical and temperature gradients that occur during heat treatment. During heat treatment, obviously, we have heat transfer. Here we have like the convection. Q equal to HA delta T here at the surface, modeling the heat transfer from the surface of the part. A lot of carburization models go into the process, including carbide formation and dissolution, and being able to map those carbon profiles into the model is very important. We'll talk a little bit more about that. Obviously, kinetics models in our databases is really our strength here. So we can capture these phase transformations that occur in real time and rate based. And so having these data is very important. And then finally, the mechanical model. Here we were talking about the mixture law here. Depending on your phases, the mechanical properties will be different. And so there's like a mixture laws to help form that. And then what you get out of it, you get out your microstructure. So this includes your phases, your hardness, and your mechanical properties for your component. For dimensional changes, we also know as distortion. We have size and shape change, depending on how the part moves. I believe 2 webinars ago, we talked about the size and shape change, so you can see that on our YouTube as well. And then residual stresses. So non-uniform thermal effects and the carbon and nitrogen effects will change the way the residual stresses map in your part. And so a little bit about the model workflow using heat treatment models here. So we like to start, if you're going to be doing carburization or nitriding, we would start with the carburization or nitriding model in order to get that carbon and nitrogen distribution in the part. And then we'll map that into a thermal model. And the thermal model will basically go through each step in the process and give you the temperature history when you run that model. And that temperature history will be used in conjunction with the carbon and nitrogen distribution to make the stress model. This is a static stress model, so we get out of that distortion, residual stress, and all the microstructural phases. Here we have that same plot with the martensite being formed under the case, the compressive stress that's formed from that martensite transformation, a little bit of the tension at the surface from the expansion of the martensite under the surface, and then we also have a contour here that shows the carbon profile to show that it is carburized and it is like kind of base material here. Now, once we get that distortion, residual stress, and microstructural phases, we got to map them in, right? So we developed a keyword here for map sol. So anytime that you finished your stress model and you want to move to a loading model, you would just activate this flag in Dante, and then it would be ready to go. Whether you're using Abaqus or Ansys, you can map the solutions and the solution-dependent variables to the models. In Abaqus, it's a little straightforward. You just use the star map solution keyword in the Abaqus. And then for Ansys, we use an initial state or init state command. And what this does is it writes out an external IST file, and all the heat treatment modeling results are included in that. And then when you read that into the loading model, it brings in all the stress and loading for that. And then so for the loading model is you can do several different ways here. You could run the implicit loading models using Dante material with map sol, and that'll map in your carbon, your phases, your residual stress. It'll have all the kind of the mechanical properties that are built in with Dante, including your modulus elasticity, Poisson's ratio properties here. And then another way you can do this is through a coordinate-based residual stress tensor. So you can map out that stress tensor and then bring that into your loading model, but you do lose out on the advantages of Dante here with the carbon and phases and stuff like that. For nonlinear cases, the BCJ model that we use accounts for the phase, carbon, strain rate, and the temperature to determine the yield. And a little bit more on that is on the next slide. And so that's an ISV or internal state variable model that we use. It includes kinematic hardening to help describe the stresses and strains a lot more accurately. The BCJ model is great for high strain rate applications, and this is awesome for us when we have phase transformations. Is usually a pretty quick rate for that, so it captures that transformation pretty well. The plasticity model determines the yield as a function of strain, rate, temperature, carbon, and phase. The Young's modulus, Poisson's ratio, and the coefficient of thermal expansion are defined as various functions of temperature, carbon, and phase. And then the loading models can use Dante to account for this material condition. And some of the advantages of Dante here is with this model, we can capture interesting things like the Browshinger effect, to where if you load material in one direction, and then you have the yield, and then you load it in the opposite direction, you have a lower yield than what you did previously. That's kind of due to the slip planes and stuff like that, but the model does capture that pretty well here. Another thing, again, we do capture pretty well, and that kind of helps us to predict residual stress and distortion, is the material strain change from phase transformation. And it's not just the austenite and the martensite like we talked about earlier, it's also phase transformation due to like volume shrinkage from iron carbides coarsening or tempering, or anything along those lines. So the model does a really good job of capturing these, and it's good to map those into other models, the loading models afterwards. So prior to the loading models, several aspects of the heat treat need to be tuned and validated. You should always be validating what you get out. If you run a couple models and you get into a result, and then you run an experiment to see how it works, and something is different, then you need to go look into your boundary conditions or look into make sure you're capturing every step of the process in order to get these validations before you start mapping into a loading model. And so some characterization things that we like to use for carbon profile, we like to use LECO or OES to measure the carbon content, and you can see carbons at the top here. You can see kind of like how the profile would look with the carbon mapped through LECO or OES, and then you would do your measure versus predicted as normal. Hardness measurements, they're pretty straightforward. You all sorts of hardness measurements in dead machines that can be used. DANTE uses the Vickers and HRC mainly for the two main hardness measurements. Thermocouple data is really invaluable because it really helps you with the thermal boundary conditions during heat treatment. So the heat up during the furnace, the quenching rate, characterizing all that is really useful for heat treatment models. And really those are probably one of the most important aspects of capturing the distortion treatment. We also do a lot of dialtometry, X-ray diffraction, and optical for phases and transformation kinetics. So you use these to validate those. And the big one we're talking about today is residual stress, again with XRD or hole drilling or slitting methods are really popular for those methods for quantifying residual stress. And then finally, distortion measurements, kind of why this hearing is here, is, measuring the distortion is really a big part of the residual stress, because the strains inherent in it cause the residual stress in the part. And then you want to make sure that you have a good validation, between the residual stress, hardness, and everything before you continue with loading models. This work was done in the proceedings about 2006. So we have these on our website if you'd like, in our publication section, to look more into these. Residual stress validation. So you don't need to use a whole gear to really validate residual stress here. A lot of times they can be used on simplified coupon geometries. This work here was done with little cylinders to show the difference here in residual stress between snap tempered and fully tempered conditions. Another one here was these bending test samples here with carburized surfaces. And the FEA model can be used to predict the residual stress in these samples geometry very effectively. This one had three different quenching regimes here, configurations that had different residual stress output for each one of these. And then you can kind of see from there, you go into your predicted, and you can see and adjust your models depending on what you need to do to validate this residual stress. And then you can take that directly into a full model once you have this validated. And you can kind of see that in more hard to reach locations like the roots of the tooth here, where the curvature of the tooth root there is smaller than the kind of the aperture window of XRD. So it makes it kind of difficult to get the residual stress in those regions. So sample geometry is really useful if you're just starting out. And then we kind of move into the case here. We have a little case study of a little 3-point bending model. Kind of similar, but without the notch than the last one we just showed there. This sample is a 10 millimeter by 10 millimeter by 100 millimeter length. We are using fixed simple supports here at the bottom, and then a loaded pad here at the top to apply the load to the rigid tooling to the part. We use a half model for symmetry. Always try to use symmetry whenever you do modeling. It really speeds up the modeling process here. Although for this one, it probably was a little overkill, but since it's such a small model, but it worked pretty well for us. We're using AISI 4120 material in the DANTE database for this work here. We applied a 2200 Newton load, or about almost 500 pounds, to the loaded surface here. And then we looked at two different models here, one without heat treating results, so it's just basically the base property of the material, and then one where with heat treated results with carbon phase and stress. So we ran through a whole carburization process here. I'll show that in the next slide here. And then it was much to capture this, like we talked about earlier. We really want to have like a layer of fine elements right at the surface here, and hopefully this translates well to your computer. You can see that there is a bunch of elements in the direction from the surface that'll help capture that carbon and temperature gradients during the process. The model workflow, again, is pretty similar to what we talked about earlier. We usually start with a carburization model and then map that carbon into the thermal model. And then that thermal model plus the carbon goes into the static structural model. And then one of them was ran without heat treatment. And then that residual stress was mapped into the loading model here for this one. So we have one without and one with heat treatment stresses. So a little bit on the heat treatment model description here. So again, the process, it's using AISI 4120. We used a furnace heating and carburizing for 6 hours at 900 degrees C. The carbon potential was 0.8 weight percent carbon, and we were kind of targeting like a 0.85 millimeter case depth with this 0.35 carbon here. That is then quenched here. If you see the graph, it was quenched in agitated oil at 65 C for about 10 minutes. And then it was allowed to cool to room temperature before tempering for 2 hours at 200 degrees C, and then a final air cool to get it back to room temperature here. Again, it was modeled sequentially, like we talked about earlier, the gas carburization, the thermal, and the stress models. And then the tooling components were suppressed during the heat treatment model, and then we applied them to the actual loading model at this time. So a little bit about the results here. So in the as quench condition, we're showing for the carburized model here about 10% retained austenite, which is further reduced to tempered martensite after tempering, obviously. We have carbon and hardness gradient is developed from the case to the core here. You can see the carbon in the yellow line here. We have about a little almost to the 0.8 in the atmosphere here, and then it goes down to the 0.2, the 4120 here, as you go to the core. And then the hardness gradient here, we got about 60 HRC at the surface, and as it goes towards the core, it goes below 50 HRC. The important thing here is the residual compressive stress at the surface due to carburization here. You can see at the top and bottom surfaces here, we have about 407 MPa of compression from this process. And you can see the other contours here for carbon content, hardness, and then the tempered martensite volume fraction. It's mainly all tempered martensite, even through the core here, since it's such a small sample. And then so for the base carbon sample, we would have a load model here. So this is no initial residual stress from heat treatment. So this is kind of blank before the load is applied. This contour is showed with the load applied here. And we can see that we obviously expect bottom tension here. As this is being pushed down, we have a little bit of a compression here, and these ends kind of want to curl up a little bit from this load. And so it pulls this bottom surface into tension here. The bending stress is pretty much as you would see from the book. It's just MC over I, and it comes out to be 310 MPa. So your moment, your direction, or your distance from the neutral axis, and then your moment of inertia here for the MC over I here. So it gives us about 310 in compressions, or in tension here on the bottom surface is kind of what we can expect. And again, the heat treatment loading model mapped in. You can see the contour of it loaded in before loading, before actually applying the load, sorry. And that still has that about 400 MPa compression. So we applied the bending load here, and the same 310 MPa tension is now about 100 MPa in compression. So basically, it's 1-to-1 to 407 minus, say, the 310 from, or plus, for that matter, from heat treatment gives us about 100 in compression here. And that illustrates the offset of the loading, the tension from the compressive residual stress that we obtained from heat treatment. Showing that a little bit easier in a graph here, this is the top surface, and then this would be the bottom surface here on the right. And it shows the loading cases here. First, we have the non-carburized sample here, and we can see it starts off in like compression from the load here, goes to tension here about halfway, and then it has about that 300 MPa or so in tension on the bottom surface. With the green line here, you can see that we start off, this is just heat treatment, this is not loaded stresses yet. We can see we start off with the green, we have compression on the outsides and tension offsetting it on the core of the part. And we can see the 400 MPa compression at the bottom surface that we start with. And then the orange line here shows the carburized loaded model. It shows the compression from the load, and then it shows the surface stress here is about 100 MPa from the load it being pushed up. Interestingly enough, the tension under the case is kind of amplified a little bit, and it's actually a little bit higher than the surface stress of the non-loaded model here. So it's really important to kind of see your case depth and make sure you have a deep enough case depth to make sure that this isn't an issue here during loading. Okay, so that was a simple model here, and then we have another case here. This was from a paper that was done in 2013. Again, the sources here. These are on our website if you'd like to see them in the publication section. This study looks at the effect of the carbon case depth. So like we talked about, you make sure that your case depth is deep enough so you don't have to worry about the tension that's under the case during loading. So 3 carbon case depths were targeted here, a 0.5 millimeter, 1 millimeter, and then a 1.5 millimeter case depth. And you can see the carbon fraction profile in the flank and then in the root here path plots for this work. One thing to note is you can see for the 0.5 millimeter root and flank, these 2 blue lines here are pretty close to each other, and there would be a little bit of less carbon from this LPC process in the root of the tooth, because on the final diffuse it has a little more area to diffuse into, and it lowers the surface carbon. As you go deeper and deeper, this gets larger and larger, the difference here between the flank and the root surface carbon. It's pretty interesting and something to take into account when you're developing carburization schedules. So the work here, this is vacuum carburized, the oil quench to harden, went through a cryogenic treatment, and then a double temper for this Pyreware 53 gear. So some interesting things looking at the different case depth here. So the deeper carbon in the case in the root produces a higher residual compression here. And then the root compression is higher here in the flank than it is due to the stress concentration here in the root. And we're looking at about 1,000 MPa root compression here between these numbers here. The stress in the flank decreases with the increased case depth, which is kind of the opposite of what we've seen there. And we can see the case depth here in the flank. The compression is highest with the 0.5 millimeter blue line here, and then it goes down to about 400 MPa here for the 1.5 millimeter. So there is a little bit of differences here in the compression that was achieved based on those case depths. The reason you have more of the compression in the root here is because of the geometry. You kind of have like a tighter radius there and helps push against each other, increasing the compression. So for this one, the single tooth bending loading model, so the residual stresses were mapped into the model. You can see where the load was applied here. And then we can see the bending stresses here in the root fillet here, high bending stresses here. So the max applied force for this was about 11,000 newtons. It's actually pretty high load here. I believe they were targeting to try to get close to yield as they could, just to see if there was any issues or anything during this process here. And then, so there's a with and without residual stress. So the red line here is the residual stress-free loaded condition here. And we can see we have a 1,800 or so MPa tension from that loading process. And then the decrease in that surface tension from each one of the carburization depths here. And we can see that the one with the highest stress, highest tensile stress here was the lowest case. And then as it goes deeper, it has a little bit of a deeper case here. One thing to note, again, is the profile under the carbon case, where you have the compression, you have to have the tension to offset it. It's somewhere inside the part. And a lot of times directly under it, we see a lot more tension. And so we see that tension more in the lower case depth here. You can see that there is a larger effect here of tension under the surface than it is at the actual surface for that part. So the residual stress offset here is about 900 or so MPa in tension. Again, it's pretty much kind of one-to-one with what we've seen before for the levels of compression. And lastly, you don't just look at the compression in the root for bending. You also have to look at the contact stresses as well to make sure that those aren't going to be issues here. We can see a plot with these two plots here. This one has residual heat treatment stresses that were built into it. And then these other three here would be stress-free conditions for the loading. So the applied torque was really high, and it was set to produce a similar root fillet stress in the single tooth bending model that we showed earlier. These are all reported in MECE stresses. So the MECE stresses are the highest, really below the contact region here in the flank. You can kind of see the residual stresses here, not from heat treatment, being much larger here from the loading here. And then you can see from the plot, this kind of burgundy or purple line here indicates the without heat treatment stresses. So if it was done without the heat treatment residual stress, we do see some sort of plastic deformation here just under the surface with the models that were performed. We can see that with heat treatment residual stresses, this does bring down the magnitudes severely with this green line here. And then we can see what those heat treatment compressive stresses actually are. This blue line here is kind of here for reference. And so is the red line for carbon for the 1 millimeter case depth. So it's really important to kind of see the heat treatment residual stresses, not only in bending, but also in the gear contact to make sure that they'll be acceptable. And then we have like a little bit of animation here. I always like to kind of show a little bit of animation. It's not really spectacular, but does show a load being applied to the actual gears here. And if we go all the way to the end here, we can see the differences between the stress-free gear here and then the residual stress for heat treatment. You can see that the compression here really helped reduce the magnitude of bending stresses in the gear root between these two cases. And you can see, I'll play it one more time here. You can see as it starts, the compressive stresses kind of give way to a little bit of tension here in the OOP direction. Okay, in summary, so the FEA modeling is used to estimate the part performance, but typically people use isotropic material properties through the loading. Many critical parts are case hardened or carburized, altering the residual stress state and material condition. DANTE predicts the part material response to heat treatment, and the results can be mapped directly into the implicit loading models. Residual stress is important as it can mitigate or exacerbate the stresses reduced in the part from loading. Carbon and phase dependencies and mechanical properties like yield, Young's modulus, and so can also be considered in DANTE loading models. And then the capability for the modeling the different cases like overload and straightening or the effect of machining on the stress rebalance can all be captured through FEA modeling. That's all I had for the webinar here today. A little quick one. I will take any questions that you may have. But if not, you can always go to our website, dante-solutions.com. We have a lot of case studies and papers there that describe a lot of the modeling processes that we do. You can also shoot us an email at support@dante-solutions.com. And let me know if you have any questions. Q&A section here. Does the mapping include distortion? Carly?
Yeah, I can answer this question. So there are several approaches, either including distortion or not. The most recommended approach does include distortion from the, let's say, heat treating model, you have distortion. And this approach uses Abaqus solver and the star map solutions keyword or feature. So the being mapped geometry included the distortion. And the mapping to geometry, let's say if you have the distorted geometry, then the map is 100%, like a mapping perfectly. But the mapping to geometry, if you have a machining or geometry change, then the mapping will be based on the distorted geometry to a new geometry. So they don't have to be the same geometry. And this approach also has the advantage of considering the carbon profile, the phase fraction profile. Let's say if loading or service model, if you have um, the different properties because of the phases, so this approach can be more convenient and easier. So.
Yeah, that's great. Yeah, so using this method, we can do both. If you're mapping to a distorted geometry, or if you're mapping to another geometry that fits inside that, the map solves method will work. If you're doing it like we did with our example here, this is modeled directly in, so the distortions will just be carried over through the loading in Ansys, like you see here. Good. Any other questions? Okay. It looks like it. Like I said, if you have any other questions, give us a call or send us an email at support@dante-solutions.com, or visit our website. Thank you for attending the webinar, and hope you have a good day.